Okay. Good morning, everyone. We are Group 13, and today we are...
Anita, right?
Yeah. Today we are going to talk about the illogical physics scenes in the Spider-Man Homecoming.
Okay.
The thing I'm going to talk about is Spider-Man passed through fire caused by airplane crash without a scratch. And here is the movie scene. Okay, and we can see in the movie scene the Spider-Man running through the fire without wearing any protective gear. And this raised the question if such an action matched with the law of the physics. And the temperature of the fire typically ranged from 800 to 1,200 degrees Celsius. And we assuming the fire is at the midpoint, the temperature would be 1,000 degrees Celsius. And we use the Boltzmann formula. The Boltzmann formula equation is used to calculate the heat radiation intensity per unit area caused by fire temperatures on the human body or item surface. And there is a formula. And P represents the radiant heat intensity, and sigma is Boltzmann constant, and T is the temperature, and the temperature we assume is 1,000 degrees Celsius, and here is the Boltzmann constant. And after calculation, the radiant heat intensity is approximately 150,000 if we assume the temperature is 1,000.
Okay.
And the maximum limit that human skin can withstand is 2,000. And the radiant heat intensity exists around 50,000 that the clothing will catch fire. So here is the 1,000 degrees Celsius, the radiant heat intensity. And here is the 800 degrees Celsius and 1,200 degrees Celsius. So when the fire's radiant heat intensity reach 150,000, the human body will suffer third-degree burns, causing irreversible and fatal injuries, while the clothing will catch fire rapidly. So through the above data, it can be concluded that the energy caused by the fire is far greater than what the human body and clothing can withstand. Therefore, Spider-Man running through the fire without any protective gear is inconsistent with physical laws.
Okay. Very good, Anita. What about the velocity? So, like, for example, people can catch fire if it's quick, right? Have you seen, like, magicians with a candle and they touch it, like, very quickly, then it's not so hot?
Because the time is short, but we can see in the scene the Spider-Man have a long time in the fire.
Okay, so in your report, can you estimate, how does the damage depend on the speed?
Okay.
And say if you run like Usain Bolt, can you go through? Can you estimate that in a report, please?
Okay.
Okay, very good, Anita. Thank you very much.
I'm Polly.
Polly, okay.
Yeah, and I'm going to talk about the scene that Spider-Man clung to and climbed on the surface of an airplane. And this is a video. And I think the thing is unreasonable because of the air resistance. I calculate the dynamic pressure. First, I assume the airplane's cruising speed is 900 kilometers per hour, equals 250 meters per second. And I assume his body's projected area is about 0.5 square meters. The air density is 1.225 kilogram per cubic meters at sea level, and is slightly lower at high altitude, but it won't significantly affect the result. And I use these formulas to calculate the dynamic pressure and the force the Spider-Man would experience. Spider-Man would experience a force of 19,000 newtons, which makes it difficult for him to remain stable or climb. And Spider-Man's ability to cling to surfaces likely relies on van der Waals forces, similar to how gecko feet function. And I calculate the minimum adhesion force required to counteract wind resistance. So the required adhesion force must more than 19,000 newtons. And then I'm going to calculate the frictional force. Spider-Man must overcome the issue of insufficient friction to move. And so I assume the coefficient of kinetic friction of the airplane's surface is 0.5. It's a reasonable value for the aluminum alloy and human skin contact. And the normal force from Spider-Man's adhesion is adhesion force. And this indicates that the friction force Spider-Man could use is only 5,700 newtons, far less than the wind resistance force for 19,000 newtons, meaning he would slide uncontrollably.
How do you calculate F friction? Can you explain the second line of the equation? How do you calculate this 19,000 newton is the power from the previous one, right? Force
it's
one, right?
previous one. 0.3 times 19,000 is the friction force.
Oh, okay, I see.
And in addition, at such altitude, the air pressure is low and the oxygen is greatly reduced. Also, the temperature is very low. So based on the above calculations, the movie scene is nearly impossible. In reality, he would be blown off by the wind, frozen by the extreme cold, or incapacitated due to the lack of oxygen. And I make a video of what happened in reality.
Excellent. Please make sure to include a link to the report, please. Okay, so I have a question about that friction. So you multiply 0.3, right? In force and 0.3, right?
Yeah.
So if that's 0.3, it doesn't matter what the force is. Any force is going to be smaller, right? Friction is always smaller than the force, right?
Oh.
So it doesn't matter with the force. So you cannot stay on the airplane with the friction.
As it's move.
Okay.
It's move on the airplane.
Okay. So now the gecko is not staying on the wall because of this, no? Not because of the friction. Because it's friction, it's always smaller than the force.
Oh.
So gecko is not this equation. So in your report, can you figure out how geckos stay on the wall?
Okay.
It's not friction.
Okay.
Okay, but good, excellent movie. Okay, next.
This scene I want to talk about is he jumping over the fence. Do I need to play it again?
Sorry, can you read that again?
Okay.
Okay. So what's the name?
Kiki.
Kiki, okay.
Okay. First, I assume the fence is 2.5 meters high, and the jumping distance is 2 meters. And using the kinematic equations, we can calculate the velocity in vertical and horizontal direction separately. So using these equations, we can, I first determine the velocity in vertical directions, and after the vertical velocity in vertical direction is 7 meters per second, and so I can calculate the time he need to spend to jump over the fence is 1.428 meters per second, and then I can calculate the velocity in horizontal direction is 1.401 meters per second. And combining these, I can get the initial velocity should be 7.139 meters per second. And but in realistic, the human's limit jumping speed is around 3 to 4 meters per second. And since 7.139 meters per second is much higher than this range, I believe this scenario is unrealistic. And I took a video if it happens in realistic.
Good. Oh, you did it yourself.
I think it has a trouble. The video is like I just jump over this high, so I can.
So your problem.
but I'm a normal human.
Oh, normal.
Yeah.
Okay. Okay. Can you include a link to this video in your report?
Okay.
Because I want to watch it.
Okay.
If it's your normal or not.
Okay.
Okay. So I have a question. Can you go back to the equation? So the world record of, can you go back?
The world record is around 6 meters per second. It's the athlete.
Yeah. So world record of high jump is, I think, 2.4 meters or so.
No, it's the world. I search for the athletes' jumping ability is like the velocity will be around 6 meters per second. So it is still much higher.
Okay. So now I think that 2 meters is a problem because high jumpers can jump, but not. I think it's okay. You can jump 2.5 meters. but then not at the same going to 2 meter. So I think that's the problem. So, okay, now can you calculate? So you calculate so figure out the world record speed and then see how far he can jump. Because I think if it's not 2 meter, but it's very close, people can do it. I mean, some people.
Oh, you mean
Maybe not
longer?
You, but
like
more talented people can do. So can you calculate that in the report?
you mean if the distance is longer than 2 meters
Distance is smaller than 2 meters.
or more than 2 meters? Okay.
So what's the velocity of the world record?
Like around 6.
Yeah, okay, so let's around 6, I mean, get the accurate number and then see how far he can jump. Can you calculate? Yeah.
If he need to achieve the 2.5 meters?
Yes,
Okay.
yes. Thank you very much.
Thank you.
It's very nice. Your
Charlene, yes. I'm going to talk about things that I think human arms cannot withstand such a huge pulling force. Suppose the ship is 70 meters long, 12 meters wide, and 20 meters high. The ship's weight can be approximated by calculating its displacement using the formula. Assume the draft depth is 4 meters and the whole shape coefficient is 0.7, and we can know that the ship will weigh about 2,300. The whole shape coefficients.
How do you get it?
I search for the normal passenger ship.
Okay.
It's about 0.7.
What coefficient again?
Whole shape coefficients.
Okay.
And based on the movie scenes, the spider web is connected to the floor of the second story from the top. So we assume the Spider-Man's point of force application is located at 6 meters from the ship's top. And in addition, a stable ship will have its center of gravity near the water line. So I assume the ship's center of gravity is 4 meters from the bottom. Suppose Spider-Man's web is tough, unbreakable, and non-stretchable. And according to the principle of leverage, we can know that Spider-Man will need to exert a force of 372 tons.
How do you get that? How do you get 672? So can you explain that 3 lines or equations? There are 4 webs. 1, 2, 3, 4.
This is the half of ship's weight,
Okay.
and the Spider-Man is, the ship is total is 20 meter high. So here is 14, and Spider-Man pull here.
The 4 meter is what?
Here.
From ship's center of gravity, and then? So what
And
is
then
4 meter? Yeah.
Here.
Yeah, from what to what?
From the
center of weight is the triangle, right? The bottom is, right?
Here is the center of weight.
Okay,
And this
then-
is the
Oh, that's the point where ship is separating.
yes, yes,
Okay,
yes.
I see. Okay, and then Spider-Man is at 14 meters. So force it's a little bit smaller. Okay. Go ahead.
However, human arms cannot withstand such a huge pulling force. Although the strength of human arms can withstand it varies from person to person. But once it reaches 1 ton, the arm would essentially be torn off.
Okay, so in your report, can you calculate how much human arms can support?
Okay.
Okay. And then also, maybe the spider web is connected. If the spider web is connected, it is okay. Can you calculate in your report?
Okay.
There are 2 things I asked, okay? It's okay? Okay, good. Charlie.
Hello everyone, my name is Eleni. Report what I want to say today is all objects are influenced by gravitational force, and this is a movie scene. And my problem is, why could Spider-Man move horizontally on the wall without any vertical movement? Because we all know that there's an important force, gravitational force on the Earth, and I think he would be affected by it. And the reasonable scenario would be that Spider-Man moves downward due to gravitational force.
So can you play the movie again? What do you mean horizontal movement? So in the wall and like this?
Yeah.
That's what's okay.
And I assume without any additional external force acting on Spider-Man, and this is my calculation. The equation of motion for vertical displacement is x equals vt plus 1 minus 2 multiply gt squared. And his total movement duration in the screen is approximately 1 second, and g is gravitational force is 9.8 meter minus second squared, and his initial vertical velocity is 0. And after calculation, we can obtain x is 4.9. And my conclusion is Spider-Man would descend 4.9 meter duration during the movement due to gravitational force, and in a condition without other external force. And this is thing follow correct physics law. And I think he would descend like me.
Okay, good. You guys are much weaker than Spider-Man. But okay. You're too weak. So Spider-Man is touching the wall, right?
Yeah.
And then moving horizontally, right?
Yeah.
He can push it downwards too, no?
No. He just jumped and then he moved to the other wall. And it is too far. It's
No, I
impossible.
mean, he jumped a little bit upward, no? Then it's okay. No?
He should distance. This.
If he just up, he's. So you say Spider-Man is stupid, right? But he can just upwards, no?
No.
Okay. So you have some hole, right? And then you want to jump through a hole like this, right? And then you go upwards, no? You go straight and I cannot. You don't do that, right?
Can you say it again?
So you have a hole here, right? See the hole. And you want to jump through the hole, right? And then you jump a little bit upwards, right? Because you know you are going to fall. You are not going to like, let's go straight and I fall in the hole. You don't do that, right? So can you play it again? Let's check it again. See, it's going a little bit upwards, no?
Okay.
Okay, but it's good. I like the movie. Okay, good. Go ahead, Annie. Yes, please make sure to include the link to your report.
Okay.
Do we
Thanks.
go to Chelsea? Okay.
Hi, so I'm going to talk about how strong should spider scale be to support a 70 kilograms Spider-Man.
Very interesting.
And the thing is like this. As you can see, the Spider-Man effortlessly just climbing on the ceiling and didn't fall down.
Right.
So let's do a little bit calculation. Let's assume that each fingertip, the total contact of the surface is 10 fingers and 2 feet. So that's assume that each finger's contact 1 square centimeters and each foot's so contact area is 15 square centimeters. So the total contact area equals 40 square centimeters, and assume that the weight of the Spider-Man is 70 kilograms. So the total force affected by the gravity is 686 Newton. Use the pressure formula, we can get that the total pressure equals 171,500 Pascal. But the natural spider scales cannot support this amount of Pascal because the natural spider scale didn't strong enough to support these.
So what is spider silk? Is it a web? Thread?
No, I think
Or the skin?
yes. I think that the is the kind of glue, like, and
Okay.
that prevent the Spider-Man from falling down to the ground.
Glue.
Yes.
Okay.
But I use the term spider scale.
Okay.
Okay, so next, where I will discuss some existing technologies that is bio-inspired, that is adhesive structures that can actually prevent a man from falling down to the ground. There's gecko adhesion pads and beetles adhesion pads and octopus suction cup and removal suction disc. And this is inspiration for the scientists to create some special glue that can do this.
Okay.
So the application on these kind of glue is industrial automation that is used to assemble the electronic devices. That the glue can assemble the glue, and advanced manufacturing is to grab conclusion.
Okay. So now you calculate the force, right? Can you go back? So what's the conclusion from here?
A conclusion from here is at the atmosphere pressure is 1.
Can spider silk hold the weight of the Spider-Man on it?
No.
Why? Why not?
Because it's not strong enough.
Okay, how strong it needs to be? How strong?
It's less than the atmosphere pressure.
No. Okay, it's good you calculate the number, right?
Yeah.
This pressure, this is what's needed, right?
Yes.
But then now you need to compare. Can you go to the next page? Next. Compare with this. So can you put all the numbers here for these natural method? And then compare with that number and then see which one is bigger, right?
Yes. And this is bigger.
Then it's okay, then Spider-Man can hold on.
Oh, no, the spider scale cannot, but these can.
Well, I mean, you're saying that Spider-Man is same as Gecko, right? Do you understand the logic?
Yeah.
If Spider-Man uses the same mechanism as Gecko, then he can stay, right?
Yeah.
Because this is strong.
No. I think the picture means that the scientists inspired by these and create another.
I know that. But the problem is you don't have numbers here. You have numbers and then compare numbers.
Okay.
Could you do that in the report?
Yes.
Okay, good. We still have the number, right? Who was talking about Gecko? Polly. Why are you hiding? You are hiding like that. Polly, what's the number for Gecko? You calculated. So you didn't? Oh, you're not listening. You calculate, okay.
Okay.
Chelsea. Okay, good, Chelsea. Next, you have a quiz or what?
I'm the last one.
I know. Okay, you guys please join. You guys are a group 12, is that right? What group? 14. Why I'm alone? Okay. Okay, you guys are not supposed to do this. You know that, right?
Yes.
Okay, are we done? We done? Okay, let's get started. Chelsea made this quiz?
Yeah.
Okay, good. The green is the same. Green and yellow are the same. Anyway, let's go. It is?
No, the answer is none of the book. The centripetal is not gravity. Centripetal is moving, right?
Yeah. Who made this quiz?
I don't know.
Can you explain?
Because gravitational force is central. It's not upward. Yeah, and scalar is not. It doesn't have direction.
Yeah, but it's also not yellow, right? So the correct answer should be green. Okay, next
Okay, I'm
quiz.
sorry.
Fine, fine. It's why we're just learning. Okay. Which one? The one. Yep. Okay, good. Oh, good. Congratulations. Okay, so one second. Get the bonus points from here, and I thank you very much for the 30. Very good presentation. Okay, now next group please set up quickly. Let's start.